great pleasure to introduce the first speaker of this workshop, Nathanan Tantivasadakarn, who will speak about non-invertible self-duality symmetries on a tensor product of space.
So thank you for the invitation to give a talk here. I'm also very excited to be at Cambridge, and also Rajath asked me to give the first talk, so I'll try to keep everyone awake when there's no coffee. Okay, so today I'm going to talk about non-invertible symmetries on a tensor product Hilbert space, so I'll be on the lattice. And so this work is some joint work with Renai Goratla and Shuheng Shao, and this work has already been published. This is also based on some ongoing work with Oracle Chatterjee and Dachuan Lu, which hopefully will appear soon. And today, what I'm going to be talking about is symmetries. And sort of symmetries is sort of a ubiquitous topic because it sort of spans many subfields, including mathematics and physics, both high energy, condensed matter, quantum information. People think about this. And for me, I am a condensed matter physicist, and I also work on quantum information. But hopefully today, I'll sort of try to explore these territories where all of these intersect. So in particular, what I'm going to be talking about today is related to the Ising model. And sort of this is the path. This is t is a function of time where I'm going to talk about different stuff. I'm going to start with the Ising model and try to relate this to gauging, which is sort of like a concept which is also in the intersection of all these. And then I'm going to switch into more quantum information things and talk about something called ZX calculus and try to make all the way to mathematics of Hopf algebras. And then I'm going to come back here and try to generalize the Ising model. And then towards the end, maybe talk a bit about quantum criticality if I get there. So just to start, I'm going to be talking about duality transformations. And roughly, what is a duality transformation? You can think of it as trying to view the same system at a different angle. And this might offer some insight to its properties. For example, you might have this as a description A of a system. You use a duality, and you find that in this dual description, it might look completely different. But maybe studying it using this description B could be simpler and might shed light on properties of description A. And it's even more interesting if you can sort of tune some parameter in your system, and you can sort of rotate one to the other, right? And you find that after you perform this transformation, after you tune this, the two sides swap into each other. Now, why is this an interesting thing? I'm going to be talking about generalized symmetries today. And since it's a defects program, I'm just going to mention that for generalized symmetries, we think of nowadays, we think of it as a topological defect in the sense that we have some symmetry, and it doesn't matter how we, as some defect, and if we sort of deform that, that shouldn't change any of our correlation functions. Now, if I Wick rotate this symmetry defect into something that acts in all of space and in a fixed time, then you can think of that as a symmetry action on your system. Okay. So now, how do we create such symmetry actions? Well, one way is, first, let us try to create a defect. So suppose I have some theory T. One way to create a defect is on half of your space, you can try to gauge a symmetry that is present in your system. So after I gauge symmetry T, I could create a defect as an interface between that theory T and a theory T where I gauge a symmetry A. And now this side of this side on the top might be a totally different theory, right? As I've shown in this picture here, you might have some description here. After you gauge it, it looks totally different. Now the interesting thing is now this defect is not yet a symmetry, right? Because it's just an interface between T and another theory, sort of T mod A, which is a different theory. But if you can tune the parameters such that you can re-identify T mod A, right, with T again, right, then this becomes a symmetry of your system. And what I'm going to be talking about today is how we can create these so-called self-duality symmetries as a topological defect. Of course, this is in the continuum, but this is the picture I want you to have when we go to the lattice. Now, the most famous example of such a self-duality symmetry is in the transverse field Ising model. And this is a 1+1D system, and I'm going to be mostly focusing on the Hamiltonian picture in today's talk. The transverse field Ising model has the following Hamiltonian. So you have a spin chain where you have two competing terms. One is an Ising term, ZZ, where Z is the Pauli matrix here. And so that's ZZ, which forces spins to try to align to each other. And a disorder term, which is given by Pauli X, which tries to bring this system into a paramagnet. So the phase diagram of this, as I tune H, looks as follows. If H is 0, then I only have the Ising term, and all the spins will want to align to each other. So you get a ferromagnet. So you get a ground state degeneracy of 2, where all the spins are up or all the spins are down. If H is infinity, then you get a paramagnet where all the spins are aligned to the right. And it is known that if you tune to these parameters, the ferromagnet and the paramagnet meet at a critical point when this H is equal to 1. Okay, so you can think of this as the ferromagnet being on one side, the paramagnet on the other side. And what's interesting is that there is an explicit transformation called the Kreimas-Wanda duality, which flips the role of ZZ and X. So after I perform this transformation, you go to a so-called dual Hamiltonian, where after you flip ZZ and X and rescale the Hamiltonian by its H, you find that the role of ZZ and X is swapped. So whatever was the ferromagnet became the paramagnet on the other side. And so what we want to, and what is interesting is if you tune these parameters, right, the ferromagnet and the paramagnet, they match at this critical point here. And so, and if you tune all the way, the paramagnet and the ferromagnet switch sides. And so it's interesting that from this duality, we can infer that if there's a transition happening in our system, it occurs when the value is right in the middle, which is where we have this critical point. So the moral of this is that this operation, D Kreimas-Wanda, becomes an exact symmetry at the critical point of this Hamiltonian. So this is an example of how a self-duality symmetry, well, I haven't explained what this operator is precisely on the lattice yet. I'll get that to a bit. But the point is that this becomes an exact symmetry at the critical point of this Hamiltonian. Okay. So the organizers asked me to sort of ask a broad motivating question. So here's mine for this talk. So I'm going to be focusing on the lattice in 1+1D, and I want to ask, suppose we have a symmetry, could be based on a group, could be beyond that based on some categorical symmetry. The question is, when does such a symmetry admit an exact lattice realization on a tensor product Hilbert space? Let me try to break this down a bit. So there are many lattice models that people can write down, but today I'm going to be asking, suppose I impose myself that I want my Hilbert space to be factorizable into a tensor product. So you have different sites, and you can write it as a tensor product of each local site. The question is, when can I have such a symmetry in 1+1D? Do all symmetries invertible, non-invertible? Can I realize them on a tensor product Hilbert space? And now the answer is known that for invertible symmetries, we're pretty confident that you can realize such symmetries on a tensor product Hilbert space, even anomalous ones, for example. More generally, people have talked about non-invertible symmetries, and people have shown that if it's the representation of some Hopf algebra, for example, you can also realize. This point is not important. I just wanted to explain what people know about in this field. But what is beyond that? What is our current compromise for the most general symmetry? So for example, there are examples where people construct general non-invertible symmetries based on a fusion category, but the tensor product is not, the Hilbert space is not a tensor product. For example, there is this anion chain construction in which the Hilbert space does not factorize into a tensor product. You're in some sort of constrained subspace, and this symmetry acts on that constrained subspace. And there are even more weirder examples where it is a tensor product subspace using some Weave-Koff algebra construction, but the trivial object does not act as an identity operator, so it's also weird in its own way. On the other hand, there are also another weird peculiarity, which will happen in the Kramers-Wanier duality that I'll talk about today, is that the symmetry, when you write it in the UV on the lattice, sometimes even though you have a nice looking symmetry in the IR, in the continuum, in the UV, when you try to write it on the lattice, it has to mix with some lattice symmetry, for example, lattice translation. And that sort of seems to be some funny sort of obstruction to realize it in its usual manner. Like when you try to put it on a tensor product Hilbert space, it's unavoidable that it will mix with lattice translation. This is not, there's no contradiction in this appearance of lattice translation, because as you flow back into the continuum, this lattice translation acts trivially. So once you go back there, it's gone, and you recover the usual fusion category symmetry you're used to. Okay, so today I'm going to be talking about trying to make some progress on this front, which is how we can construct these non-invertible symmetries in a tensor product space. So I'm going to be talking about ways in which we can use sort of these dualities and self-dualities to try to write down new forms of symmetries, especially non-invertible symmetries, on a tensor product Hilbert space. So that gives us more constructions of these non-invertible symmetries explicitly. So as I mentioned, generalizing the first thing, which people have already done, which is some simple generalization of this Kramers-Wanier duality. You can, for example, gauge a abelian symmetry, which is obviously self-dual. And this duality transformation becomes a non-invertible symmetry at the self-dual point. So generalizing this notion of Ising, you can get something that is related to, for example, these Tambara-Yamagami fusion categories. Right. So just changing a Z2 to an abelian group will give you this type of non-invertible symmetries. The second type is to start with a non-abelian symmetry and try to gauge it. You don't end up back at the same theory, because a non-abelian symmetry, after gauging, you actually get a non-invertible symmetry based on the representations of groups. So it's a different beast altogether. But nevertheless, this also gives us a way to construct new non-invertible symmetries. Now, after reviewing these two aspects, what I want to do today is sort of combine these two ideas together. And I'm going to be starting with a non-invertible symmetry in which I can gauge. I'm going to gauge this whole symmetry such that, I'm going to pick this non-invertible symmetry such that I arrive back at myself. So this will be gauging a non-invertible symmetry to arrive back at a non-invertible symmetry. And this will give rise to an even bigger non-invertible symmetry. So let me also emphasize that a lot of these ideas at the mathematics level or as a fusion category is already well studied. What I'm trying to do today is just try to put everything on the lattice. So that'll be my goal. Okay. Are there any questions so far? Yeah.
There's a recent Polish paper which is explaining that
Yes. So right. So I think the claim there is exactly. I'll come back to this point at the end. Maybe if you could wait till then. Okay.
So when you mentioned exact realization of a lattice, the word exact doesn't mean you don't want it to mix with the lattice translation, like the previous.
Sorry, when I said exact.
Like the exact lattice realization of a symmetry on the lattice.
I will allow mixing with lattice translation. So these ones that are sort of self-dual, they will mix with lattice translation. Yes.
I'm actually confused of what you mean by an exact tensor product Hilbert space. Even if you have something like the Ising model,
yes,
this doesn't have a tensor product space because you have to specify the charge, whether it's even or not.
Oh, you mean the charge sector? But in the Hamiltonian, I don't need to specify, right?
makes it working. So why do you insist on having this tensor product structure?
When I define the Ising model, I don't need to fix my charge sector, right? So the Hamiltonian has both.
No, but if you start doing duality transformation, you have to. Otherwise, it's not.
Yes. When I do the duality, it'll mix these up, and that's why you have to kill, and that's why it makes it non-invertible. So the Kramer's 1A duality becomes non-invertible if I put it on it. If I restrict to the subsector, it'll be a Z2 symmetry, and it's invertible.
You should start with a non-passive product filter space in the beginning, and you should fix the charge sector.
Oh, but then in that case, the symmetry will become invertible again.
Sure.
Right. So it will not be that's not the purpose of what I want to do. So I want to have it as the Ising, the Kramer's 1A duality, be a non-invertible symmetry, and it flows to the sigma in the Ising.
All these non-invertible symmetries can also be embedded on a tensor product filter space.
I agree.
Which
But
is very similar to saying, okay, I just work with a fixed charge sector. So I don't understand the philosophy of saying, okay, this is local, this is tensor product structure, this is not. It's just a different way of saying what are the sectors. But why do you insist on having this tensor product structure?
just because I'm fixing on a particular Hamiltonian, right? So I just want to ask, what are these Hamiltonians which commute with certain symmetries, right? So the Hamiltonian will have both charge sectors. Maybe we can discuss it. Yes, John.
I did have the same kind of thing, a comment. So any other chain, you can also make it a tensor product. Just adding another term to enforce the future. So
yes, I agree.
It's not completely clear.
Yeah, indeed.
I think that's because, of course, you can add it, but the symmetry only acts in that subspace, right? It does not act on the full Hilbert space. Okay. Any other questions? Right. So the context of my talk is just, for now, I want to fix my Hilbert space and talk about operators which commute with Hamiltonians in that Hilbert space. Okay. So just before I continue, I just want to mention sort of a conspiracy theory. It's maybe a bit hard to look at, but it's sort of relating sort of different things that have popped up in the community, relating what I'm going to talk about today. So it's actually relating. Today I'm going to be talking about self-duality and using a mathematical tool called ZX calculus, and that has appeared in the context of quantum computation. But also different ideas have also appeared relating to the cluster state, the fact that the cluster state is a symmetry-protected topological phase, and the fact that they can be used for gauging, and also related to this quantum double model and Hopf algebra. So there's a lot of sort of different things that have popped up in different fields in the community. This talk was sort of try to generalize this to sort of the non-abelian version, and sort of that'll be sort of filling this corner over here. So this is the outline of my talk. So first I'm going to be talking about ZX calculus and how do we use it to describe the Kramer's 1A duality as a non-invertible symmetry. Then I'm going to generalize this to the non-abelian gauging, and then I'm going to be studying a non-invertible symmetry in sort of this non-abelian generalization of the clocks or the Potts model. Okay. So let me just begin by talking about ZX calculus. So what is ZX calculus? This is a graphical tool that can be used to construct linear maps between two-dimensional systems or qubits. And it has recently been very popular in quantum information, in particular for compiling quantum circuits and using them for fault-tolerant quantum computation. So it's a sort of diagrammatic calculus which allows you to show that different quantum processes are sort of equivalent by deforming these gluing these nodes and deforming them together. And apparently, you can even teach it to your kids these days. Actually, there's a book for kids called Quantum in Picture. Here it says, "Hey, I'm a spider." So you can actually teach this to your kid. So I'm going to try to whiz through that within 5 minutes. Hopefully, this will be simple enough. So a crash course. I'm going to be introducing 2 tensors. So this is a 3-leg tensor, so you should think of it as a state with 3 inputs, right? And this is basically a GHZ state. So this is all 0 plus all 1. So this just means that as a tensor, when it enforces I equal to J and also J equal to K, abstractly like this. But if you're a condensed matter physicist, for example, you would just think of this as a ferromagnet on 3 sites, if you will. And now, the red one is sort of in the dual basis. So instead of 0 and 1, I'm going to be using plus and minus. So plus here refers to 0 plus 1, and minus refers to 0 minus 1. And if you expand that back out in the 0 and 1 basis, what you find is that it's enforcing I, J, and K to sum up to 0 mod 2. Okay, so I'm just going to call this the sum tensor because J plus K is equal to I mod 2. And here I'm going to call this the copy tensor because whatever I put in I here is going to get copied into J and K. If you're familiar with Hopf algebras, this is nothing but the co-multiplication and multiplication of Z2. I'm going to get back to this in a bit. But some people also call this the GHZ tensor because GHZ is this 3-body 0, 0, 0 plus 1, 1, 1. And as a mnemonic, you can remember which one, if you're confused which base is which, green stands for GHZ. So that's the 0, 0, 0 plus 1, 1, 1. And red is just the dual basis. And these tensors satisfy certain properties. For example, if I have the green tensor, you know that if I flip all the spins here, then this state remains invariant, right? So if I apply a poly X on all the 3 legs, it does nothing to this state. Also, we know that this state is sort of related to the Ising model, right? It's sort of like a ground state of a three-site Ising model. So if I apply ZZ, right, a Z would give a minus sign to each one, but if I only apply even number of them, then this also leaves this state invariant. So you can act Z on 2 of the 3 legs. That'll also keep it invariant. In the dual basis, you just need to swap Z with X. So Z on all sites does nothing, and also X on 2 sites does nothing. Okay. Now more generally, you can construct bigger GHZ states with more legs. That'll just be more zeros plus more ones. And then the dual one with more legs. And you can also, I'm also going to be using this yellow box to refer to the Hadamard, which is the Z2 Fourier transform. It just swaps the X and Z basis. So some examples that might be interesting, if you have what is a 1-leg tensor, then this is just 0 plus 1 up to some normalization. I'm sort of going to be I'm sort of going to drop the normalization from now on, but for example, this 1-leg green tensor is the plus state, which is because it's 0 plus 1. Okay. The nice thing about these diagrams is that once you glue them together, so gluing these tensors together means contracting indices. And once I glue them together, it turns out that the topology doesn't matter. So I can sort of deform this tensor any way I want, and it still gives me the same linear process. So for example, if you happen to know some quantum information, this gate is exactly what is called the C0 gate. What it does is if I have inputs A and B, what this green tensor does is it copies the value of A and B, right? So it copies the value of A, so you have 2 A's now. And then this is a sum tensor, so it adds A to A plus B. So whatever value is here gets added into the second leg. So this is so-called the C0 gate in quantum information. And these tensors satisfy certain rewrite rules. You can, if you have sort of a GHZ state or a ferromagnet, you glue 2 of them together. Of course, you get a bigger GHZ state. And you can also, there are a bunch of sort of rules here which you can use to transform one type of tensor into another type of tensor. If you're familiar with Hopf algebras, these are sort of these bi-algebra rules or Hopf rules for your Hopf algebra specific to the case of Z2. Okay, and Hadamard or Z2 Fourier transform turns red into green. Okay, so what do I want to use these states for? I want to use these to construct a interesting state or a wave function, many-body wave function. For example, one can use this to construct the so-called cluster state, which is a famous state in condensed matter and quantum information. What is the cluster state? The cluster state is just a state on a 1D chain, which is the +1 eigenvalue of ZXZ. So this is the unique state that satisfies ZXZ on nearest neighbor sites to be equal to +1 on every site. And it turns out, how do you build the wave function for this? You can actually build it out by gluing these tensors together. So I took these green tensors, glued them with Hadamard, and it turns out that this is exactly the wave function of the cluster state. The way to see that is to use these properties of these identities I just mentioned. So I mentioned that, for example, if I have z on 2 legs, that acts as nothing, right? So if I have z on 1 leg, it means I can push it to any other arbitrary leg. So it means that, let's try acting zxz on this wave function. If I push z in, I can push it to the right here. If I push it through Hadamard, it becomes x, right? And I can do the same for this side. And now you can use the fact that if I have x on all the 3 legs of the green tensor, it acts as identity. So zxz is equal to 1 on this state. So I've shown you that this state is the unique state which satisfies zxz equal to 1 on all the sites. Okay. And this is the so-called cluster state, and it has 2 interesting symmetries. One of them is if you product on all the odd sites here, you will notice that if I product zxz on all the odd sites, all the z's will cancel. So I have a global z2 symmetry which acts on all the odd sites, similar for the even sites. Okay. A similar looking state I'll be talking about is if I perform a Hadamard or Fourier transform on all the even sites. This will just change x to z, and this will change these 2 z's to x. And so this is a cousin state which has zzz equal to 1 on all the odd sites, and zzz equal to 1 on all the even sites, and xxx equal to 1 on all the odd sites. Okay. And this is so-called the CSS cluster state. CSS is just an acronym for 3 people, Kauderbank, Shor, and Steen. That's just a technical term to say that these terms that are stabilizing my state are all either pure Z type or pure X type. Okay. Why are people interested in the cluster state? It's because it is an example in condensed matter of a symmetry protected topological phase, in the sense that if I end this chain on an open boundary, then on the boundary you will find a projective representation. In more high energy speak, you can say that the edge, which is a 0 plus 1D theory, has an anomaly generated by Z2 times Z2, this H2 class, so it's a projective representation. How do we see that? We can actually apply the symmetry in the bulk. So I apply X on all the odd sites, and if I push that onto the edge, I will see that using these identities, you can show that you get only X on the left edge and X on the right edge. If you do that similarly for the Z, you push that, you'll find that you only get Z on the left and the right edge. So usual linear representation actually factors into 2 projective representations. And the fact that these commuted before, but now in the boundary, they actually anti-commute, is the signature of this projective representation. So this is one cute way that people use to study these states and see that there's explicitly an anomaly when you go to the boundary. Okay. So far, so good. Should I pause here again if there are any other questions? Okay. So if not, let me now connect back to what I wanted to talk about, which is the Kramers-Wani duality. Okay. So just to give a bit more context before we head back, this Kramers-Wani duality, as I mentioned, is an exact symmetry of this Hamiltonian, of this 1D transverse to Ising model with this particular coupling, such that you're at the critical point. And in the continuum, we know that this Kramers-Wani duality becomes the symmetry of the low energy of this Hamiltonian, which describes the Ising CFT. Now, of course, the corresponding symmetry is just the Ising fusion category. There are 3 simple objects, 1, psi, and sigma, and they have the following fusion rules. And they sort of inherit their properties from the lattice equivalence that I will talk about soon. So the global Z2 symmetry, which is a global spin flip, will flow to this psi. And this Kramers-Wani will flow to sigma, which obeys these fusion rules. But now I'm going to go back to the lattice and see, it's secretly more subtle if you do it on the lattice. on the lattice, what happens is, in addition to a Z2 symmetry, you also actually have lattice translation, which is the symmetry of this Hamiltonian. And now, the Kramers-Wanier duality, very schematically, as I said, it swaps x and zz. But on the lattice, what happens is you have this operator d, in which if you push x through, it becomes zz. But if you push zz through to the other side, it actually becomes x on the next side. So a consequence of that is that on the lattice, if you square this operator, you don't get one, you get 1 plus eta, but you also tag along a lattice translation symmetry. So that's sort of a puzzling thing that, and people have actually shown in these later papers that on the lattice, if you want to write down Kramers-Wanier on a tensor product Hilbert space, you must extend it by translation symmetries. Okay. There's no way to get up this translation symmetry. So this translation symmetry in the continuum will just act trivially, and you get back sigma times sigma is 1 plus psi, but on the lattice, you have to mix with lattice translation. Okay. So I just told you how this operator d acts, but not what the operator is. Let me show you how to get this operator. And the answer is just to go back to this cluster state. I mentioned this state, which is stabilized by xxx on the odd sides, zzz on the even sides. I'm just going to flip. This is a state right now. I'm just going to flip half the legs down, and now you see that if I push zz through, it becomes z. If I put x through, it becomes xx. And now if I swap z back to x and xx back to zz, that's exactly Kramers-Wanier duality. So the Kramers-Wanier is actually closely related to the cluster state for this regard. You just turn this state into an operator. Okay. So now I want to relate this Kramers-Wanier operator to maybe a more familiar process, which is gauging, to show that how this is related to gauging explicitly on the lattice. Before that, I need to make a very pedantic point, which will sort of become important, is that there are actually two Z2 symmetries that I'm interested in. One is the usual Z2 symmetry, which you are used to, which acts as the product of X. The other one, I'm just going to call it a rep Z2 symmetry. And if you already know too much, you will know that Z2 and rep Z2 are actually isomorphic, but I'm going to be pedantic about this point because I'm going to have them act differently. I'm going to have Z2 act as the group action, so it's going to shift the shift group elements, so it's going to act as a poly X. Whereas rep Z2, there are two elements. There's a trivial irrep and the sign irrep, and the sign irrep is going to give a minus sign to the 1 instead of the and not the 0. So that's why I'm going to put it as a poly Z. So this is just a pedantic point just to distinguish between these two symmetries. We know they are isomorphic because there exists a Z2 Fourier transform, which is this operator relating the two. But this will become important in a bit. The reason I want to do this is because when we gauge a Z2 symmetry, we would actually get a rep Z2 symmetry as a result. And then only afterwards we re-identify rep Z2 with Z2. So I'm going to try to make that explicit on the lattice. So let me claim that this operator that I mentioned before, which I get from flipping this cluster state, is the operator that gauges a Z2 symmetry. Why? Because in one side, I showed that it has a Z2 symmetry, and if I push the Z2 symmetry, it sort of disappears into the other side. So you can sort of say that this Z2 symmetry has been gauged. As an output, this output has a rep Z2 symmetry because if I push all the Z's in, it also disappears. Okay. So this is just the reason, but let me try to explain in more detail why this is related to gauging, although it's the correct answer. I'm going to use ZX calculus to deform this diagram into this. You can convince yourselves that these two are equivalent because, as I mentioned, these greens can all fuse together into one big green there, and these reds can all fuse back up into there. The reason I break this down is to sort of show you the gauging process explicitly. So I have an input sort of wave function that I can put in into these legs here. And what I'm going to show is that you can think of this as your matter field. I'm going to introduce some gauge fields, and I'm going to sort of minimal couple them in some sense. And then I'm going to perform a projection which projects you into the gauge invariant subspace. That's what this operator is doing. And let me show you that this is precisely this operation. So, as I mentioned, we're going to add certain gauge fields, initialize in the 0 state. Sorry, this is a typo. This should be E. I initialize 0 on all the sort of, you can think of this as a 1D graph with vertices and edges. I initialize these gauge fields on the edges. Then I perform a basis transformation, which you can think of sort of as entangling this SPT state. If you're a field theorist, you might think of this SPT as some background action, a background response to putting in a background gauge field, right? And for two types of Z2s, you can sort of couple them together with sort of this cup product type of action. And in the end, you're going to sum over all these background gauge fields to make the gauge field dynamical. And then that's exactly this projection over here. On the lattice, what we're doing is this. You can think of this as sort of a basis transformation such that I project into the correct gauge invariant subspace. I'm going to impose my Gauss law, and this operation as a whole is projecting into that subspace. And at the end of the day, after you massage this, well, that is exactly this transformation, which, so hopefully I convince you that this operation is what is gauging a Z2 symmetry and is giving you a dual rep Z2 symmetry. Okay, but we're not done yet because I started from a certain Hilbert space on the vertices, and here I sort of ended up with a Hilbert space on the edges, right, and with a different type of symmetry. So in order to make it a self-duality operator, currently it's a map, right, from the vertices to the edges. To make it an operator back onto the same Hilbert space, I need to do a few more steps. So after I identify, I perform this gauging. For example, I start with the Z2 Ising model with these operators. After gauging, I'm going to end up with the rep Z2 Ising model, and it's on the dual lattice. So I have to fix that. First, I need to perform this isomorphism, right, to go back to the Z2 Ising model. It's still on the dual lattice, so we do sort of this half shift to go back from the edges to the vertices, and now you're back to yourself. Okay, and now you swap X and ZZ. And this half shift is essential, right, because you need it in order to shift back from edges to vertices. And this half shift is why the Kramer's 1A operator, when you square it, gives a lattice translation, and you cannot avoid that. Okay. So that's where this this unit lattice shift came from, this half lattice shift in the Kramer's 1A operator. Okay. So you can also see that this doesn't look very symmetric, but actually I can push the Hadamard in here by changing this to green, and now this picture looks a bit more symmetric. So it's now a self-duality operator in the sense that both sides looks the same. Okay. And you can also use this ZX calculus to square this operator explicitly and show that indeed, after you square this operator, you'll get a full translation plus this projector into the even subspace. Okay. Right. So just related to Frank's comment, if you are in the even subspace, then this will act as identity, and this will just act as translation. If you ignore translation, then it's just a sort of Z2 operator in some sense. So in the continuum, this is a genuine Z2 operator in the even subspace. But if you extend it to the whole Hilbert space, you'll find that there's this projection which makes this operator non-invertible. Am I doing on time? Okay. So this is the story for Z2. Now I want to generalize to more interesting settings. For example, how do we do this for non-abelian groups? So for Z2, let me give you a picture in terms of the wave function what we're doing. So if I start with certain configurations here, say S1, S2, S3, and these are mod 2, so they are either 0 or 1, what is this map doing? This map is copying the value of this state here, and now adding them on the edges. So it's taking S1 and S2 and outputting S1 plus S2, mod 2. So you can think of this as sort of mapping to, at the level of states, it's mapping to the domain wall variables, right? If the spins are aligned or both up or both down, the output would be 0, right? But if the spins are anti-aligned, you'll get an output of 1. So this is basically telling you what the domain variables are, and this is what the trick we use, right, in the StatMech model to perform the Kramers-Wanye duality. So how do we generalize this to group G? We want to, for example, group G, we want to do the same thing, right? So we want to go to the domain wall variables. So we have G valued fields. And now we want to write down something that will take us to this domain wall variables, which is looking at the difference of group elements. So if I input G here, I'm just going to copy G, right? I need to introduce another map in the Hopf algebra. This is called an antipode. This just inverts all the group elements. And then I multiply. This will become a multiplication matrix now. And I just multiply these two together. And now this is the domain wall variable, right? I'm just looking at what is the difference between these two group elements. So this map turns out to be the map for gauging a G symmetry, because you can show that before gauging, if I apply with a left multiplication on all the input states, the output state is invariant, right? Because if I multiply G, G, G here, they're going to cancel in the middle over here, and the output wave function is the same. So this operation gauges a G symmetry, because afterward it acts trivially. What is the symmetry on the other side? We know the answer is gauging a rep G symmetry, but what does rep G symmetry look like on the lattice? Well, one way to construct it is I take the output, I product all of them together, and then I compute a character or some representation in this group. So I define some diagonal operator which takes all these as input, multiply them together, and compute the character. So it's a diagonal operator. And you see that this is invariant of whatever state I input here, right? So this operation is invariant when I push it back down. So this is a rep G symmetry in the sense that, and this is how you would write it in the sort of diagrammatic way. You would define a matrix, right? For each irrep of your group G, you copy the value of your group G, you compute its matrix element, and then you string them all together and take a trace. Okay. You can also think of it as copying the value, multiplying them all together, and then computing the character. And you can show that these operators, when you multiply them together vertically, they satisfy the fusion rules of rep G because of this character. Because character multiplies to character as they decompose according to how irreps multiply. Okay. So this is what rep G symmetry looks like on a lattice. And notice that it does not factor, even though your Hilbert space is a tensor product, it factors into a tensor product. This rep G symmetry, it does not factor. You sort of have to multiply everything first and then compute the character. In the case that G is an abelian group, it does factor, and you'll recover what is your poly Z, right? Because everything here is one-dimensional. But for a non-abelian group, there are irreps which have a dimension more than 1, and when you multiply them together, you have to sort of compute this whole thing first. Okay. So more generally, going even beyond groups, we can construct a similar diagram for a Hopf algebra. And what is a Hopf algebra? Well, a Hopf algebra is just something that has both multiplication and co-multiplication. Multiplication will be the red tensor I mentioned, and co-multiplication will be the green tensor. And now, since things might not commute, or even co-commute in this case, you have to be more careful about the orderings in which you multiply things. So I have to. So instead of these simple rules of these fusion, you have to instead use these axioms of the Hopf algebra, which is sort of associativity or unit and something like that. You still have these other axioms, and I have to introduce this so-called antipode mount, which sort of swaps the two sides. But basically, that's the diagrammatics of a Hopf algebra. And so the tool we need to construct these self-duality symmetries, I mentioned at the beginning, it's called ZX calculus. But what is ZX calculus mathematically? It turns out that it's related to something called a self-dual Frobenius Hopf algebra. So there are many words in here, so let me try to unpack that. First of all, there's a Hopf algebra, which means that there's an algebra and a co-algebra, so you can multiply and co-multiply, and there's an antipode. There is an associate Hopf algebra, which is sort of related roughly by flipping these pictures upside down. So there's another multiplication and another co-multiplication, and that are compatible in a particular way. For example, there's something called an integral, a Haar integral in a Hopf algebra, and the Haar integral of this Hopf algebra is the unit of this associated Hopf algebra, and then there's a dual version of that as well. And moreover, if you look at the green and the red part separately, they form a Frobenius algebra, which is mean they satisfy this relation. So basically, the thing I was doing for Z2 using ZX calculus earlier can be generalized to the sort of non-abelian case by going to a Frobenius Hopf algebra. So this is the structure we need to build those self-duality maps.
I'm sorry.
Yes.
H and H tilde are initially just separate Hopf algebra.
You can show that if H exists, you can always construct H tilde. I didn't specify how to construct it, but it's related to this green and you can sort of use sort of this integral to define this and its integral, which always exists, to define this dual Hopf algebra. Yeah, I didn't spell it out, but you can sort of use this together with this to sort of flip the legs upside down.
Okay, but it's on the same vector space, no?
On the same vector space, yes. Yeah. So here I'm just assuming the vector space is H itself. Yeah, yeah. Right, so it's labeled H tilde, but yeah, the algebra is the same H. Yeah.
What's the Frobenius algebra?
Yes.
What is the Frobenius structure?
Oh, the Frobenius structure is here. So for the green part, the co-multiplication of H and the multiplication of H tilde form a Frobenius algebra, and also the red guy. Yeah. So it's both Hopf and both Frobenius at the same time. And if H is self-dual, one also has a Fourier transform. The Fourier transform is what generalizes this Hadamard, this yellow matrix, and now I need to worry about the multiplication. Previously I said it changes red to green, but now it does not need to square to 1. It will square to the antipode instead, and you have sort of this compatibility structure which changes red to green, and you might have to swap the legs, the order of the legs in the most general case. Okay. So now with this whole structure, we can show that you can construct a self-duality symmetry which before and after gauging is both rep H star. So H star is just the dual of the Hopf algebra. I'm just setting this convention like this so that if I input the group algebra, I'll get back vec G, basically. So if I input H as the group algebra, this symmetry is vec G. But in the more general setting, this will give me rep H star. So you can show that this performs gauging, which takes rep H star symmetry to a rep H symmetry. And then there's this basis transformation given by this Fourier transform and then a half shift, like in the previous case. And you can show that after you do all that, before and after this operation, which is a rep H star symmetry, if you put it under and also above, they both get absorbed by this self-duality operator. So you can think of it as gauging a rep H star symmetry, and you get back rep H star after some basis transformation. And similarly to Ising, we can compute the fusion rules And we find that if you square this operator up to a translation, you will get a sum of all the irreps up to some normalization by the dimension. So roughly, this Kramers-Zwanni operator, this generalized Kramers-Zwanni operator, squares to this regular representation or regular character of this rep H star up to lattice translation. Okay. Let me pause again here. Is there any other questions?
If you pause, they do weak algebra.
Right. So the reason we're doing half algebra here is because anomaly-free fusion categories are described by as a rep of algebra. So what we're trying to gauge here are all the non-anomalous things. So we're trying to gauge a symmetry, and by imposing that it's anomaly-free, that we can gauge it, it immediately reduces to a half algebra. That's why we're considering this case.
Is that correct? About non-semi-simple.
Oh, I'm assuming semi-simple, yes. Finite semi-simple. Okay. So now that I defined this weird operator, which is self-dual, it's the self-dual operator under gauging this rep H symmetry. Let me define a Hamiltonian which commutes with that symmetry. So, like the Ising model, you can define some sort of generalized version which has some ZZ term and some X term. That's your Hamiltonian. On one side, you'll have a paramagnet, and the paramagnet is given by, on each side, you just have sort of identity or your unit of your half algebra, and it factors into the unit. And on the other side, you have a ferromagnet, which is actually constructed like this in the diagrammatic sense. Now, if you're at the midpoint, so this Hamiltonian has this rep H star as a symmetry. And at the self-dual point, you get an enlarged symmetry given by this Kramers-Zwanni, which is sort of like a Z2 extension of this rep H. And just to, as a sanity check, if we reduce it to the cyclic group case, which is this group algebra, then this rep H star is actually Vex Zn. And this will recover us back the Clock and the Potts model, which is a generalization of the Ising model, which we know has a Zn symmetry. And at the midpoint, it sort of enlarges to this Tambari-Yamagami category of Zn. Okay. Yes?
I thought in the beginning of the talk you said that you want this tensor product. It was basically because you start with a certain Hamiltonian, and then want to do what commutes with it, but now you have the symmetry and construct this Hamiltonian. So.
Oh, right. So one can go about it either way, right? One can ask, if I have a Hamiltonian, what are its symmetries? But I'm going to construct the symmetry first, and then there are different Hamiltonians which are satisfied under the symmetry. So you can also ask, right, given a symmetry, what are the possible, say, gap phases?
Yeah, but how does that? How's the motivation from the beginning then?
It's because I want to construct everything in the tensor product Hilbert space. But given a symmetry, that might or might not be possible. Here I'm showing you how, given certain symmetries, you can construct it on a tensor product Hilbert space, maybe with mixed equal lattice translation. And here is a Hamiltonian which commutes with that symmetry. It won't cover all Hamiltonians that commute with the symmetry, but I'm just discussing sort of like some sense fixed point Hamiltonians that are easy to construct in this formalism.
For the case n equals 3 for
Yes.
the Potts model,
Yeah.
is the CFT has some kind of Fibonacci symmetry that would fit in this context?
I think that'll be an emergent symmetry, so it won't be there on the lattice. Yeah. So I'm only asking, in the UV, what are the symmetries that are there? Yeah. Okay. So we know that in the cyclic case, right, we can construct this Potts clock Hamiltonian, and people have tried to do non-abelian cases, but you don't get the self-duality symmetry. Here I'm showing you that if you go to the if you are willing to go beyond groups, right, if you go to half algebras, then there are sort of non-abelian examples which will admit a self-duality. So let's look at the simplest example. So the smallest sort of non-abelian Hopf algebra in some sense is this so-called H8 Hopf algebra. The details of what the multiplication and co-multiplication are not too important. What I want to convey is that the rep of this Hopf algebra, you can think of it as some subcategory of two copies of Ising. So there's a two-dimensional object, sigma 1, sigma 2, which fuses into these four guys. So using the usual fusion rules of Ising, this subcategory is itself a fusion category, and it corresponds to rep H8. Now, naively, if you want to construct this in a lattice model, you might say, oh, it's related to Ising square, so I can just take two critical Ising chains, right? And this will be a symmetry. So indeed, in the continuum, rep H8 is a symmetry of the Ising square C of t. But on the lattice, if I write it down with two critical Ising Hamiltonians, this operator, tensor with itself, it still mixes with lattice translation, right? So the thing I want to do is actually gauge this symmetry on the lattice. But if I try to do it in two copies of the Ising Hamiltonian, I cannot do that because there's already a lattice translation, and I don't know how to gauge lattice translation. Maybe someone in the future will do that, but so far I don't know how to gauge something that mixes with lattice translation. So this version of the symmetry probably cannot be gauged on the lattice, even though once you flow into the continuum, translation disappears and you can do everything fine. So I'm sort of stuck if I try to approach it using two copies of the Ising Hamiltonian.
You say it's a proof that we cannot be gauged or just the argument?
It's proof by exhaustion. That I don't know how to gauge lattice translation.
Okay, you do not know, but
Yes,
it's
yes.
not just an argument.
Yes. So I'm not going to do that. Instead, I'm going to use the construction I gave previously, which if I just input H8 as a Hopf algebra, actually this version does not mix with lattice translation. So already there's some subtlety on the lattice where in the continuum, you might say there's one fusion category, but on the lattice, there's more than one realization, and those are not equivalent. One mixes with lattice translation, the other does not. So that's already surprising. But I'm going to use this version because I know how to gauge this one. Okay. So the claim is that let me construct this this sort of generalized Ising model with this rep H8 symmetry. Along this whole line where I have the x term competing with the zz term, I will have this rep H8 symmetry. And at the self-dual point, I'm going to get this extra enlarged symmetry. Now, what does the phase diagram look like? On this side, at the fixed point, we will have a paramagnet, so everything is disordered. And on the other side, we break the symmetry spontaneously, and it turns out that rep H8, there are 5 irreps, so the ground state degeneracy is 5. Okay. This is the Hamiltonian. Currently, I only have the two-dimensional rep, but I can also add other terms, and this is what we find numerically. This is not to scale. I just sketched the rough phase diagram, but it all looks pretty interesting. It seems that what we're finding here looks like some first-order transition, but as you crank up the terms which have the 1D irreps, you find that there are actually some intermediate phase which you can also go through. So for example, from the trivial state, you can go through an Ising transition to a state with 2-fold degeneracy, and then to another phase with 4-fold degeneracy, and then lastly, another transition to this 5-fold degeneracy. And all of these are Ising transition, it seems. We're currently trying to pinpoint this point here, which seems that all these lines meet, and try to figure out what this multicritical point, but we're still trying to do more numerics on it to figure out what exactly is this phase over here. Okay, so let me wrap up now. So at the beginning of my talk, yes.
This picture, you were saying you were doing some numerical work, but this picture overall is a mathematical statement?
No. It's just what we see from numerics, and I roughly draw. This is not even a straight line. I just drew a straight line, but it's some curve.
But regional divisions like this?
Yes, the regional.
You can prove that?
No, I don't know how to prove that. Okay. Yes. So I only studied one example, the smallest one, but of course now there are infinite more self-dual half algebras, which people can of course are welcome to go study. So let me wrap up now. So in the beginning of the talk, I posed the question, when does a non-invertible symmetry in a 1 plus 1D admit a lattice translation if I impose that we only realize it at tensor product Hilbert space? So here is my guess. So actually, after I realized, I wrote this, I feel that conjecture is too strong of a statement for a physicist to make instead of a mathematician. So let me change that to a suspicion. Because maybe someone will just shout out that you're wrong, you know. So this is related to Ryohei's question. So for my integral fusion categories, recently it actually has been proven that you can realize it without mixing with any lattice transformation symmetries if and only if it's an integral fusion category. So all the quantum dimensions are integer. Okay. For the Ising case, it's a weakly integral fusion category. There are square roots. And the guess is that this square root is somehow responsible for this mixing with lattice translation. So why? And as I mentioned, this rep H8, it came from two Isings. But actually, rep H8 is an integral fusion category. So there's one way to write it such that it mixes with lattice translation. But then there's another way to write it such that it doesn't. So you can avoid that by using the fact that rep H8 is secretly integral fusion category. So that's sort of interesting. And my guess is that if you go beyond that, for example, Fibonacci, maybe you cannot realize it in a tensor product Hilbert space. So that's my suspicion. In the math literature, there also seems to be some related math conjecture related to something called property F, which says that if you have a weakly integral braided fusion category, the braided group is finite. And I don't know if these two have any relations. Is it the same source of sort of this distinction between integral, weakly integral, and sort of beyond? So that seems to be something that
if this conjecture is for the weakly integral is replaced by integral fusion category.
Sorry, could you say that again?
If we replace the weakly integral with the integral fusion category, you just still have a braided group that is finite.
Oh, integral is weakly integral, right? So the braided group is finite.
It's there.
Yeah. Okay.
Sorry, can I ask a dumb question? When you say realization on a tensor product Hilbert space, you mean they should also be symmetries of some local Hamiltonian?
Yes, or just construct an operator which sort of is sort of, in this tensor network language, I would say a matrix product operator, which realizes this symmetry. So glued from local tensors.
But so you're not referring to a Hamiltonian here?
No. So this is more of the kinematics, right?
Oh,
what is the symmetry constraint, not about the dynamics. Yeah. No. Yeah.
You'll come up with the matrix product operator implementation.
Yeah.
So there's some extra rule you have that I'm kind of not totally clear on, because we have MPOs for all like fusion category and half algebra symmetries, right? I think you want an extra rule that's like,
Which is in the tensor product over space.
the identity.
Yes.
You want the identity to really act as the identity.
Yes, that's also true.
Is that the condition
Right.
for
Which,
more?
right. Because for the Wyckoff algebra, that's where it fails. Yes.
Is that the only condition, or is there more conditions?
Yeah, that could be. I'm not sure yet. It's maybe not a precisely well posed question, but
So that's necessary at least.
yes, that's necessary. Yeah. Okay. So to summarize, today I showed how to gauge this symmetry corresponding to the representation of H for any half algebra H in a tensor product Hilbert space, right? And when this half algebra is self-dual, I can define a self-duality symmetry and a corresponding generalized Ising Hamiltonian, which at the midpoint respects this self-duality symmetry. I already mentioned that these clock pot models, they're well studied. We know what the transitions are and what are the new potential critical points that we can get in these sort of non-abelian models that would be exciting to explore further. I already mentioned this point about even though fusion categories, we believe, classify all these 1 plus 1D symmetries in the continuum, right? But on the lattice, they can be realized in distinct ways. Some of them might mix with translation and some of them might not, right? So it seems that this data alone of a fusion category seems to be not enough to specify a symmetry on the lattice. So an even broader question, it becomes more and more philosophical, right, as we go thinking more and more about these subjects, but I don't even know what is a symmetry on the lattice, so let me end there.
Yeah, so you probably already maybe mentioned somewhere, but I'm lost about this. But is that I want to understand why physically it's important to know lattice mix the distance. Why is it important question to know mix or not mix?
Why is it important to know?
Can you repeat the question because we didn't understand?
Oh, the question was, why is it important to know whether it mixes or does not mix with lattice translation? I mean, in some sense, maybe one thing I can comment is when we talk about symmetries on the lattice, we want to capture all, at least back in the invertible case, we want to capture all things that are locality preserving, right? So if you have some unitaries acting on tensor product Hilbert space, you can define the notion of locality. And now translation is also a locality preserving unitary. And people also study this in the context of quantum cellular automata. So it seems that symmetries on the lattice, we should take these into account as well. And it just turns out that for the Ising case, there's some unavoidable extension by this lattice translation. So in order to generalize invertible symmetries to non-invertible symmetries on the lattice, it seems that we should generalize the notion of what is a locality preserving unitary or quantum cellular automaton to the lattice. So that's why it automatically includes translation in there.
Does this mixing procedure affect how you can gauge it or not gauging it?
When it mixes, I don't know how to gauge it.
Oh, maybe that's one indicator that is.
Right, but yeah. My point is just that in the continuum, there's one symmetry like rep H8, but on the lattice, there are two different types. One of which I know how to gauge on the lattice, but the other I don't know how to gauge. And I don't even think they can be connected, right, through some locality preserving transformation. So they are distinct. So at the UV level, there seems to be two different symmetries which are not the same symmetry. And in the continuum, they also become the same. There's also a converse, which I didn't talk about, is that this Kramers-Wanne duality, you might ask whether it's Ising or SU2 level 2 on the lattice. And it turns out it seems you cannot do that because of this mixing with translation, because you cannot define properly a Frobenius-Schur indicator. And people like Shuheng and Nati have constructed lattice models for which Kramers-Wanne is a symmetry. And in the IR, one of them flows to Ising in the continuum, and the other one flows to SU2 level 2 in the continuum. So the same lattice operator flows to different fusion categories in the continuum. So it seems this map is not injective nor surjective. This lattice symmetries and continuum symmetries.
Yeah, I have a question about the Hamiltonian. So this generic Ising-like model, like, okay, you don't even need to specify the Hopf algebra, right? You just use the fact it's self-dual at this point. But then it's like it's pretty horrible if you're writing down explicitly. So if you specialize to H8, if you use specifically the isomorphism to its dual, which is canonical.
Is it specify what, sir?
Well, because right now you don't really need to specify the Hopf algebra, really, right? You just use the fact that it's self-dual. Mm-hmm. So if you specialize to H8, then you write down like a more sensible Hamiltonian.
On an 8-dimensional Hilbert space.
Like minimal Hamiltonian that would have the self-duality.
You can write it down, but it looks pretty awful, yeah. Also, an interesting thing is that this ZZ term is usually in the abelian case, it's a diagonal matrix. The Z here is not diagonal anymore, coming from the fact that the co-multiplication does not copy things anymore. So it's a bit horrendous looking. That's why I didn't write it down explicitly.
Then maybe it's not the only self-dual model. Maybe you can write down another simpler self-dual model for H8.
That's true. It could be possible. It's just that we wrote it down based on the construction of generalizing X and ZZ to Hopf algebra. So X corresponds to multiplication, right, and Z corresponds to co-multiplication.
Do you have similar conjectures in higher dimension where you have more QC and more like lattice symmetry?
Yeah, right. There's not at the moment. I don't know how to. Maybe someone can tell me about higher Hopf algebras or something, and then maybe it can be generalized. So far, I don't know how to generalize it.
Perhaps in view of the time, I suggest we ask any more questions over coffee, which should have arrived just outside. Yeah, so let's thank Nat again, and we reconvene at 11.